Section 4.6 is related rates. So we've got some stuff to write down first, and then we'll talk about it. Again, write down what you feel is necessary for you, but some of this is important. So the first thing, of course, is to understand the problem. But this is really important. The first thing we want to do is identify the variable whose rate of change you seek and the variable or variables whose rate of change you know. So it's really important at the beginning of each of these problems to write down the rates that you know and the rate that you're looking for. Drawing pictures is helpful on most of these. It will help you to set up an equation. The third thing you do is write the equation relating the variable whose rate of change you seek with the variables whose rate of change you know. So again, this relates directly back to this first step. Differentiate both sides of the equation implicitly with respect to time. So we're going to do d dt, and so everything will be implicit. Don't forget your chain rule, because you are going to be using a new variable dt. Fifth, substitute any values or quantities that depend on time. Anything that is a point in time can only be done after you differentiate. If you put in a particular point of time prior to differentiating, it becomes a constant and you'll end up with zeros and you can't solve the problem. The last thing is to interpret the solution, make sure you have the right units, and make sure that it makes sense. All right, we're going to do 3 examples. First one. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving east. When the cruiser is 0.8 miles north of the intersection and the car is 0.6 miles to the east, the police determine with radar that the distance between them and the car is increasing at 15 miles per hour. If the cruiser is moving at 60 miles an hour at the instant of measurement, what is the speed of the car? So I've got a couple of rates here, 15 miles per hour and 60 miles per hour. So let's draw a picture and see what we can come up with. A right-angled intersection, and the police cruiser is coming from the north, and a speeding car is moving east. So this is the police, and they are moving this way, and this is the car, and it's moving this way. This part, this instant in time, we're going to save till the end. At that point, the police determine that the distance between them and the car, so if this is the police and this is the car, this distance is increasing at 15 miles per hour. That's this speed. The cruiser is moving at 60 miles per hour. Now there's a really important thing or point to make here. When we are talking about speed, we need to pay attention to whether it is positive or negative. If something is moving to the right, it's positive. If it's moving to the left, it's negative. If something is moving down, in other words, the distance from the police to this corner is decreasing, we need to make this negative. They will not put that in the body of the problem. You have to know based on whether the thing that is being measured, in this case miles, is getting smaller or larger. Okay, so I have my picture and I have some given information. I need some variables to assign to this. Since this looks like a coordinate plane, I'm going to make the car X, the cruiser Y, and the distance between the two I'm going to make Z. So I know that dz dt, distance between the police and the other car, has a rate of 15 miles per hour. I also know that the rate of the cruiser itself, dy dt, is negative 60. So those are the rates that I know. I am looking for the speed of the car. So given this information, I'm going to find dx dt at the moment when x is 0.6 and y is 0.8. These are the things that I'm going to plug in at the very end. If I plug them in too soon as a constant, then I'm losing or taking away the fact that this distance, this 0.8, is decreasing. So I know dz dt, the rate of change between the place and the car. I know the speed of the cruiser, dy dt. I want to find the speed of the car at this instant in time. This is how you should set it up. What do you know? What are you looking for? And when are you going to look for it? So we need to set up an equation using the variables on top of my rates, so x, y, and z. This is a right triangle, so I can use x squared plus y squared equals z squared. Notice I am not using my derivatives, I'm just using the variables that I need to solve my problem. All right, it's time to derivate. I'm going to derivate the whole equation with respect to t. So this will be 2x dx dt using implicit plus 2y dy dt equals 2z dz dt. I'm going to go to a new screen. So where I am is 2x dx dt, 2y, whoops, that's what I want to do, 2y dy dt equals 2z dz dt. And let me write my givens again. You don't have to repeat this. You should still have them on your page. Dx dt was negative 60. Dz dt was 15. I knew that I'm looking for this information when x is 0.6 and y is 0.8. So here's the information I have. Dx dt I know. Dz dt I know. I'm looking for dy dt. And I have information now about the instant in time that I want to find these values. So when x is 0.6, and I know dx dt is negative 60, and y is 0.8, I'm looking for dy dt, that's my unknown. And I know dz dt. Do I know z? Remember, we had a right triangle. So using a 3, 4, 5 right triangle, z should be 1.0. So although I wasn't given that distance, I can calculate it from the drawing I made. Okay, so now it's just a matter of solving. Negative 96. Oh, wait, I think I did this backwards. My x, no, my x was 0.8. I'm really sorry, go back and fix that. My y was 0.6. I knew something looked wrong. 0.8. Okay, so if this is 0.8 and that's 0.6, this was 1.2, dy dt equals 30. Solving this equation, adding 96, dividing by 1.2, dy dt is 105. So that tells me that the car is moving at 105 miles per hour at this moment in time. All right, let's try another one. Water runs into a conical tank at a rate of 9 square feet per minute. Tank stands point down has a height of 10 feet and a radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So I have a rate of change. Oh, this should have been cubic feet. 9 cubic feet per minute. The water is running to the tank. That is a rate of change of volume. Volume of water. dV dt equals 9. The water is increasing, so it's positive. I need to find, it's the only rate I know, I need to find how fast the water level is rising. So I'm going to call that dH dt, and I want to find that when h equals 6. So again, I'm looking for an equation for volume with height. Well, I know that volume of a cone is 1/3 pi r squared h. I don't have a rate of change for radius here, so I need to somehow get rid of that r so that my equation is just in terms of v and h. I know from my picture that r is 1/2 of h. Using similar triangles, no matter what my height is, my radius will always be half. So I can substitute that in for r. So my equation now becomes volume equals 1/3 pi r squared h, which is 1/3 pi 1/4 h cubed. So I'm going to write it finally as pi over 12 h cubed. So now I have an equation in terms of v and h, and I want to find dH dt. So derivate. dV dt equals pi over 12 times 3h squared dH dt. Substituting in the values that I know. dV dt is 9. That's a positive. My dH dt should be positive also because my height should be increasing. Equals, I'm going to consolidate this to pi over 4 times, when h is 6, 6 squared times dH dt, my unknown. So 9 equals pi over 4 times 36 is 9 pi. Divide both sides by 9 pi, and dH dt equals 1 over pi. So the height is rising at a rate of 1 over pi, or approximately 1 over 3.14, etc. Okay? All right. One more. A hot air balloon is rising straight up from a level field and is tracked by a rangefinder 500 feet from the liftoff point. All right, I'm going to draw my balloon with my little basket. It is rising, so it is going up, and I have a rangefinder over here that is 500 feet away. That is a constant. That is not going to change. The rangefinder is not moving. Excuse me. So I can use that as a constant. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing, so for an angle increasing, I'm going to call that d theta dt. That's a rate of change. Is 0.14, so the angle is getting bigger. How fast is the balloon rising at that moment? Now, they didn't give me the moment exactly, but they kind of did back over here. So how fast is the balloon rising? That's what I'm looking for. So I need a variable here. I'm going to call it y. So I want to find dy dt. When theta equals pi over 4. So I know d theta dt, I want dy dt, and I want to find it when theta is pi over 4. So I need an equation with theta and y. This is a constant, so I can use that as a number. So I look at this picture and I think, well, theta, my angle here, is related to y in 500 using the tangent formula. So my formula that I'm going to write is that the tangent of theta is y over 500. Okay? So I'm ready to derivate. Secant squared theta d theta dt, there's what equals 1/500th of dy dt. And I know that. So I want to find all of this. I've got my derivation. Now I plug in what I know. I know d theta dt. This is the instant when I am finding this, so I'm going to use pi over 4. Secant squared of pi over 4 is 2. So I'm going to do the rest of my equation. Multiplying both sides by 500 will give me my dy dt. And sticking that in my calculator, I get dy dt equals 140 radians per minute. Okay? So there's 3 examples. We will work on this in class, clearly, and we'll see how things go. The following slides are a chapter summary or test that this particular textbook adds in. I'm going to just scroll through it. If, as you're preparing for your chapter test, you want to look at some of these problems, please feel free to come back to this video and use them. So there's one on increasing and decreasing in concavity. And as you'll see, the next slide, the slides at the end will give the answers. So again, max and mins, derivative that passes through a particular point, linearization. This is all stuff we've done. Again, secant lines and tangent lines, linearization and approximate values again, and then a related rates, actually 2 related rates problems. So if you want to use these later, please feel free. One more related rate, and then here are the answers.